Hi, my name is Dmitry. I'm a software engineer and Python and C++ mentor. This is the second video in the series that I'm making that I call Saving Expired Software with Explicit State Management. In this video, we're going to talk about software complexity, the two types of software complexity, and how we use software design to manage that software complexity. But before we jump right into it, let's talk briefly about why the software complexity matters so much and why we want to discuss it in the first place. So why does complexity matter? Uh, the main reason here is quite simple. It affects most of the aspects of software engineering. So the more complex the software is, the harder it is to read and understand its source code, add new features without breaking existing behavior, predict how the system will behave under real load, reason about its internal state, and therefore debug it when something inevitably goes wrong. So in short, that basically covers most of the basic functions that we as software engineers are carry out on our daily to-day jobs. And so to summarize this, I would say that the more complex the software is, the less efficiently we, the software engineers, can work with it. That means not being able to deliver quality software on time that is both efficient and reliable. So next, I'm going to talk about software complexity and the two types of software complexity that kind of comprise the overall software complexity. The first type is going to be domain complexity. And that is basically the complexity of the problem that the software is aiming to solve or help other people solve. So, for example, if we're talking about writing a weather forecast system, to do that, you have to understand the weather forecast models, and you kind of cannot get around this, right? Because it's that domain complexity that makes your application actually useful to other people and useful as a thing in general, right? If you are using a weather forecast system, you actually want it to forecast the system, which is impossible to do without understanding the weather forecast models. So it's the quality with which you're able to understand the domain complexity and are able to ingest it that determines how well your application is gonna perform in terms of its actual usefulness, its actual function that it carries out. And so, for example, we can consider this function that I wrote here in Python. I tried to make it as concise as I could. And that basically, all it does is it computes a value of a polynomial by extrapolating it based on the point values that I've been given. And the x is the point, is the argument where we are trying to kind of find the value of the polynomial. And you can go through the code here. And again, I tried to make it as concise as I could, but still you have to understand a bit of math and how the method works to actually be able to figure out uh, that it works and internalize that function such that you can debug it, you can refactor it, you can change it, and so on. Now we're going to talk about the second type of software complexity, and that is the overhead complexity or the accidental complexity. It's not how the software behaves, but it's how the software is laid out. So what does it mean? So we have this domain complexity, right? The domain complexity is normally quite high, right? And so your application is solving a problem that is real problem. And when we're doing that, we cannot reduce that complexity, but we can manage it. And what does it mean to manage it is to lay it out in a way that kind of makes sense to people, to software engineers that read that code so that they can internalize that thing better. It's kind of the same as a good lecturer in a university will structure their course in such a way that even if the subject is complex, it will be easier and more natural for their students to understand it. So overhead complexity comes into play when the lecturer doesn't do a good job of laying out their structure of the course, and so the structure of the course ends up being poor and not well prepared to actually give the material to the students, and that makes the entire course less understandable, take more effort to understand and internalize by the students, even though the domain and the theorems are the same, everything is the same, it's just how it's laid out. That same concept applies to software very well. Um, so let's have a look at this function on the left. Can you understand what this code does? And like, how long will it take you to understand that piece of code? You can write it down in the comments. For me, the answer is going to be, it's going to take me much longer than the original version of the function, which is exactly the same as I showed you the previous time. So those two functions do the exact same thing. They have the same behavior. Obviously, you have to factor in the difference in the function names and the function arguments. But other than that, they are the same. It's just that the variable names and the type annotations are missing. I mean, variable names are not missing. They're just, they don't reflect the underlying concept at all. And that makes the function just really, really tough to work with. If you were to kind of debug this function or to refactor it, it would be very hard and much harder to do than compared to that function on the right. So the point I'm trying to make here is that you can totally increase the complexity of your software without changing its function. And well, the poor naming and lack of type annotations are far from the only ways in which you can increase Python software complexity. And those, hopefully, you never see as blatant of examples as those in real life. But then there are other means by which complexity can grow that are not as apparent as what we have here. And one of them, one of the big ones there, is actually the software design. When your software is designed not is not designed to be understandable, well, that works the other way around. It becomes less understandable. So let's talk about software design a bit. First of all, I want to kind of touch on some misconceptions that people have when you talk about software design to them. Um, First of all, sometimes you can hear that certain projects don't have a design. And that's actually not true because every project has some sort of design. The question really is, it's the difference between being deliberately created and thought through or just being emergent as the code is implemented, right? If I were to write any piece of code, it's going to have some sort of design. I cannot prevent that from happening. The question is really whether I thought about that design or I just kind of wrote something that kind of works on some examples and just moved on. And that is a very important distinction. And that's how you use software design to kind of manage your complexity. So improving the design is one of the ways to manage software complexity, but it never is for free. It has its costs and it has its benefits as everything else, right? So the costs vary. Some of them are quite apparent and obvious, and some of them are more subtle. So the obvious costs are like, well, doing any additional work is always costly, but then the abstractions themselves that you sometimes introduce when designing your application, they also increase, they have some complexity of their own, and that complexity can be justified or not. So that's a question, and it's something to be maintained, let's say. And then the less obvious is like when you refactor a project to have a quote unquote better design, you actually invalidate all of the or discard all of the knowledge of other developers that were not involved in refactoring the software, so that they need to relearn the new system. And so all of those costs, they kind of pile up, and you have to have some justification for that entire process to happen. So you want to be dead sure that the benefits of refactoring your software or even putting additional effort into designing it are going to be kind of worth it. And so for many projects, actually that ends up not being the case. So like if you have a smaller project that it doesn't necessarily need a design to work well, if you can just internalize the entire thing, like, in 5 minutes, might as well not have design. You just implement it and then you go. But the thing is that making a mistake in that choice can be very costly, and it doesn't matter, like it applies both ways. If you spend too much time or on designing or refactoring something that doesn't need it, then you've just spent some months of people's work on doing something that doesn't bring much benefit and invalidates some previous knowledge and previous behavior. And so you end up paying a huge cost that you don't have a benefit to justify for. And then the other way around is that if you have a software project that would really use some like good design, um, it can be very costly to continue working in its non-designed state or even start implementing its non-designed state. And something you have to consider in that choice is future extensibility. So one thing is implementing the project, and the other thing is the lifetime of the project when you kind of um, expand it, extend it to accommodate new use cases or cover old bugs or something. All of that has its own cost, and that cost is in many ways determined by the design of the project. So the takeaway from today's video that I want you guys to have is, first, managing complexity is essential for project success. And here success is defined as reaching the goal is in minimal or close to minimal costs. Then how much to spend on software design is a trade-off, and making a wrong choice in that trade-off is a costly mistake. So now in the next video, we're going to talk about why there's a certain class of Python projects that seem to consistently make that choice incorrectly and what we can do about it. Stay tuned.